So this is Pre-Calculus, Chapter 4, Section 1, Polynomial Functions and Models. This is Part 1 of this section. Our first learning objective is to identify polynomial functions and their degree. All right, so we're going to identify polynomial functions and their degree. So if I have a polynomial function, f of x, and a sub n, x to the n power, plus a sub n minus 1, x to the n minus 1, less, depending upon how big your polynomial is, a1x plus a0. As long as my a's are real numbers and n is a non-negative integer, the domain is the set of all real numbers. So that's the big important part. Polynomial function. The domain is all real numbers. Remember when we got all that domain and range stuff? When you have a polynomial function, as long as your a's are real numbers and your degree is a non-negative integer, then your domain is all reals. All right, we're going to determine which of the following are polynomial functions, and for those that are, we're going to state the degree, and for those that are not, we're going to say why not. So take a peek at A. F of x equals 3x minus 4x to the third plus x to the 8th. Are all my exponents non-negative integers? Yes. Are all my a values real numbers? All my coefficients? Yeah. So this one gets to be a polynomial. And what degree is it? What's the highest degree? Gosh. 8. You take the highest one and he wins. It's like playing war with cards. You're like, oh. So it's a polynomial and it has degree 8. All right, well, let's look at B. G of x. X squared plus 3 over x minus 1. That's no chase here. It's not a polynomial. It's a ratio of two polynomials. Because I have a denominator, and I can't simplify, well, even if I could simplify. If I have a denominator, it's not a function. H of x equals 5. That's a hard one. Is that a polynomial? It is, because my degree is 0. Is 0 a non-negative integer? Yeah, so he qualifies. So it's like 5x to the 0, which is just 5. So when you have a constant, that is also a polynomial. All right, what do we think about f of x equals x minus 3 times x plus 2? Do we have non-negative integer exponents? Yeah, if we FOIL that out, it would definitely be a polynomial function. And it would have degree 2 because my x times x gives us an x squared. Okay. G of x is not a polynomial because 4x to the negative 1 doesn't have a non-negative integer exponent. All right, last but not least, our h of x, 1/2 x to the third minus 2/3 x squared plus 1/4 x. If you believe it's an integer, if you believe it is a polynomial, stand up. And if you are standing, then with your fingers, show me what degree it is. If you think it's a polynomial, go ahead and stand up and then declare the degree. So h is a polynomial. Its degree is 3 because it has x to the third power. So it doesn't matter that I have fractions for my a as long as I have a real number for a. I could even have a root 3, whatever. That's a real number. As long as it's a real number. All right. So let's summarize what we know about the graphs of polynomial functions. This is what we've studied so far. So a 0 function, f of x equals 0, has no degree. And it's the x-axis on your graph. A 0 degree polynomial is a constant function. F of x equals some number as long as it's not 0. And that's just a horizontal line that crosses the y-axis wherever your constant is. So if it's, we had f of x equals 5, so it would cross at 5. F of x equals -1 would cross, horizontal line crossing at 1. First degree polynomial, I have an x value with a coefficient plus a constant. As long as my coefficient, this is a linear function. If you look at a1 here, we have been calling this the slope and this the y-intercept. So this is not a new concept, it's just a different way to write the same thing that we know about, which seems to be what we've been doing these last 3 chapters. Just rewriting and restating what we already know in a more complex mathematical way. So this is a non-vertical, non-horizontal line with a slope of a1 and a y-intercept at a0. And then we have our second degree polynomial, f of x equals ax squared, a2x squared plus a1x plus a0. As long as our first guy here, first constant, or first coefficient is not 0. This is called the quadratic function. The graph is called a parabola. It opens up if a2 is greater than 0 and opens down if a2 is less than 0. All stuff we already know. All right, so for this graph, the important thing to know is that a polynomial function, so I just want you to write this down here. The graph of a polynomial function is smooth and continuous. If it is not smooth and continuous, it is not a polynomial function. It can either look like a corner or a cusp or a gap or just a hole in and of itself. If any of these things occur, it is not a polynomial. Okay, a power function of degree n is a function of the form f of x equals a x to the n, where a is a real number, n is greater than 0, and is also an integer. It's called a power function. Power functions, they lift weights. They get buffed out. So notice that there are no additional terms. It's just the one power term. That's why it's called a power function. No other bits and pieces to it, just the one term. So here's some examples. F of x equals 3x is degree 1. F of x equals -5x squared is degree 2. F of x equals 8x cubed is degree 3. And f of x equals -5x to the 4th, that's degree 4. So those are the different degree power functions. All right. So the shape of even functions, so don't write anything down right here. this is just a looky-loo item. So even functions all have the same similar shape. They're not exactly the same, but so here's our classic f of x equals x squared. And when I get x to the fourth, this is the blue one is f of x equals x to the fourth. So as you get a higher degree, and these are only for even functions, the higher degree, the kind of wider your base gets. It's a nice, almost a V shape when it's x squared, but your base gets wider and more U shaped the higher your degree gets. 8th degree, nice and almost a boxy shape to the bottom. But it's going to have one side going up to negative infinity, the other side going up to infinity, and it has a similar shape. So if you look at the different even functions, y1 equals x to the fourth is this bowl shape. y2 equals x to the 8th, it gets a little bit more U-shaped, and then x to the, or y squared equals x to the 12th is even more wider. The bottom spreads out wider. It gets more boxy. So here's what I want you to write down. Properties of power functions. If f of x equals x to the n, where n is a positive even integer, f is an even function, so its graph is symmetric with respect to the y-axis. The domain is the set of all real numbers, and the range is the set of non-negative real numbers. The graph always contains the point negative 1, 1, 0, 0, and 1, 1. As the exponent n increases in magnitude, the function increases more rapidly when x is less than negative 1 or x is greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. Or as we were saying, it gets more boxy on the bottom part there. All right, so odd functions have kind of the same principle. If you're an odd power function, you look like our little swimmer guy. So this is x to the third, y equals x to the third, goes through the points 0, 0, 1, 1, and negative 1, negative 1. If I am an odd power function with a positive coefficient, I have a similar look. I still go through the points 1, 1, 0, 0, and negative 1, negative 1, but as I am on the x-axis, I widen out just a little bit and get more boxy. So here's the cube, here's to the 5th, and then here's to the 9th is even more of a squared off shape. So I'm not having you guys write this down. This is just a look. So let's compare. Here's when we're in a spread out graphing window, so from 16 to negative 16, you can see the x cubed function comes in and has a wider look to it when you get in close. The x to the 7th comes in, boxes out a little bit more, so that way it makes a more boxy figure when you zoom in and comes out. And then the x to the 11th definitely comes in faster and then has a more dramatic curve. So it's the same, similar shape. They all go through the same 3 points, but it gets boxier on those corners. So here's what I want you to write down. F is an odd function. Its graph is symmetric with respect to the origin. So if f of x equals x to the n is a positive odd integer. The domain and range are the set of all real numbers. The graph always goes through -1, 0, 0, and 1, 1. And as the exponent n increases in magnitude, the function increases more rapidly when x is less than -1 or x is greater than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis and make a more boxy transition. All right, so let's look at graphing polynomial functions using transformations. So now we have to recall the information we learned in the previous chapter and apply it to polynomials. So if I wanted to graph 1 minus x to the 5th, x to the 5th is at a swimmer or a U shape? Swimmer shape or U shape? It's a swimmer shape. And we have a positive 1. So here's our swimmer shape. It goes through the points -1, 0, 0, and 1, 1. You guys can hold off. There's going to be a separate graph for each transformation. You would just want to graph the end result. So the negative in front of the x to the 5th says I'm going to reflect it about the x-axis. So all of my x values switch. So instead of having 1, 1, I'm going to have -1, 1. Still going to have 0, 0. But instead of having -1, 1, I'm going to have +1, -1. So it just switched my swimmer. Flip that around. And then I'm going to shift it up 1. So my graph is going to be the swimmer. He is going to be reflected, and he is going to be shifted up 1. So this final product is the one I want you guys to graph, to actually write in your notes. All right, so we're going to graph 1/2 x minus 1 to the 4th. I have to deal with this vertical compression and this horizontal shift. Which shape are we having? U shape or swimmer shape? 4th power. It's going to be a U shape. I'm going to have a horizontal shift 1 unit to the right. Anything inside the parentheses is opposite, so it's -1, so I shift to the right 1. And then I'm going to have a compression of 1/2, so it's going to flatten my U shape. So go ahead, and this is the one I want you to write in your notes. All right, and so this is going to conclude part 1 of the chapter, or the 4.1 notes.